After a considerable amount of literature research, the Mozart effect appears to be a popular topic for researchers investigating manipulations that impacted performance in spatial judgment and reasoning. We were, therefore, interested if it also had an effect on perceptual motor tasks, in our case, the Fitz task. The Mozart effect refers to the concept that people perform better on tests of spatial abilities, spatial judgment, and spatial reasoning after listening to music composed by Mozart. Many investigations inferred that listening to Mozart music prior to or during a task enhances performance on mathematical and spatial and perceptual motor abilities. Despite the short-term nature of the Mozart effect, research into the effect has received widespread attention in the popular and scientific media. Indeed, the notion that music makes you smarter has become one of the most popular investigations in psychology. In our experiment, we used the Fitz task to examine if the Mozart effect would have an influence on perceptual motor ability. To ensure our experiment was fair and controlled, each participant used the same pen for the trials, sat at the same chair and the same table, and all participants completed the trial consecutively. The target sheets had blue tack on the back to ensure that the paper did not move around during the trial. Prior to starting the experimenter verbalized the instructions to ensure the participant was clear on what to do. All participants had one practice trial, and the experimenter would begin each trial by saying, "Are you ready?" followed by "Go." The target sheet order was randomized using randomizer.org for all 30 trials. As for the results, the y-intercept is a measure of the overall speed of the perceptual motor system. To this base speed, the time to result any uncertainty is added. The y-intercept predicts how an individual will perform on a task with 0 bits of difficulty. The slope of the line is the rate at which uncertainty is resolved. Participant 1 had a y-intercept at baseline of 52.7 and at manipulation 0.21. At baseline, a correlation coefficient value of 0.922 existed, indicating a strong positive linear relationship, with an R-squared value of 0.85, where 85% of the variance between the data can be accounted for through this variable. As goes for the manipulation, participant 1 also produced a strong R value of 0.947 and an R-squared value of 0.89, or 89%. As for the calculated rate of processing, participant 1 at baseline calculated 17.06 bits per second to 15.22 bits per second during the manipulation. Participant 2 had a y-intercept at baseline of 16.429 and at manipulation negative 9.9286, also obtaining a correlation coefficient value of 0.985 at baseline. This indicates that a strong positive linear relationship is present. This is also an indication that, as the number of bits increases, as does the time taken to complete the task. With an R-squared value of 0.97, 97% of the variance between data can be accounted for through this variable. As goes for the manipulation, participant 2 also produced a strong R value of 0.944 and an R-squared value of 0.89 or 89%. At baseline, participant 2 had calculated rate of processing at 13.3 bits per second, yet this increased to 14.92 bits per second during the manipulation. This identifies that, whilst listening to Mozart, participant 2 increased their information processing speed and accounted for an additional bit per second. Participant 3 had a y-intercept at baseline of negative 86.71 and at manipulation negative 85.43. A correlation coefficient value of 0.908 at baseline, indicating again a strong positive linear relationship. With an R-squared value of 0.83, 83% of the variance between this data can be accounted for from this variable. As goes for the manipulation, participant 3 also produced a strong R value of 0.904 and an R-squared value of 0.82 or 82%. As for the calculated rate of processing, participant 3 at baseline calculated 10.28 bits per second, increasing to 11.71 bits per second during the manipulation. For the manipulation, each participant put in headphones prior to starting the first trial and pressed start 5 seconds before the experimenter said go. Each participant listened to the same song by Mozart, Sonata No. 10, which continued to play for the duration of the full experiment. The same controlled variables were used to ensure validity, the only difference being the playing of the song. We anticipated to find a decrease in performance speed on the FITS task whilst listening to Mozart's sonata. An overall decrease would be anticipated across all trials, which would then indicate a more efficient performance and therefore confirming that listening to Mozart's sonata would impact the participant's speed on completing the FITS task. Upon completion of our manipulation, a significant increase in information processing speed could be observed while listening to music during the tasks, as compared to the control group, the group who did not listen to the music. This was indicated by the decreased amount of time taken in milliseconds to complete each trial overall. Across all 3 participants, our results provided support for our hypothesis that the Mozart effect would decrease the time required to complete the FITS task. Across all 3 models, the slope of the regression line were as expected, and there was a positive correlation between the number of bits and the time taken to complete each trial. The more bits to process meant that the task was more difficult. Participant 1 on average took the most time to complete each trial, regardless of the number of bits, while Participant 3 overall had a faster information processing speed. Participant 3 results were much more sporadic and less strongly correlated. This could have been as a result of other confounding variables, such as the individual's attention span, fine motor skills, whether the participant took caffeine before the tasks, their mood, drowsiness, or any practice effects if the participant had completed a similar task previously. All of these extraneous variables could have potentially impacted our findings. Since our data set indicated a relationship between listening to Mozart, Sonata No. 10, during the FITS task and an increased information processing speed, learning environments such as schools and universities may consider implementing music into these settings in order to help to act as a booster for the human information processing system. This could potentially foster faster speeds of information processing, even in scenarios with higher numbers of bits or a more complex task. Whilst we found significant results among our 3 participants, there were a number of limitations in the study that should be considered in future replication of this experiment. It is plausible that perhaps the Mozart effect has little to do with Mozart in particular or with music in general. Rather, it may represent an example of enhanced performance caused by manipulation of arousal or mood. A helpful direction for future research would therefore be to try and further elaborate on what was tested in this study to a broader range of experimental conditions. This would help identify whether the results can be attributed to the Mozart effect itself or just an arousal increase which could be an outcome of a larger number of other variables. Further experimentation could involve altering the volume, genre of music, or type of song and perhaps even other variables which may result in arousal or mood increase. Using such a limited sample size was another limitation of our experiment, as it was difficult to extrapolate meaningful data which could be generalized to a wider population from such a small dataset. A recommendation to future research would be to use a much larger and more diverse sample size and population in order to generate more meaningful and generalizable data.